Thanks, Adam.
Thank you, Rachel. Good afternoon, everybody. I hope, first of all, you can hear me, and secondly, that you can see on your screen at the moment a blank 3x3 grid. Magic squares have fascinated me for many years, and you never stop learning. There's always something new coming my way on a regular basis. And so what I'm proposed to do in this session is a mixture of 2 or 3 things. First of all, to present to you material that I've used in live presentations in schools many times to audiences ranging from P6 upwards and to audiences of size 25 through to about 200. There's lots of things that you can do, and I'll indicate a few of them. But then we'll move on and to look at 1 or 2 things that I didn't know until comparatively recently. Now, of course, for somebody as ancient as me, comparatively recently on this occasion means about 10 years ago, or 8 years ago to be precise. And show you a little about what's going on behind the scenes. And then finally, there'll be an outburst of culture at the end for anybody who's left. So let's hit the road, and here's the task that I present live to pupils. We've got this blank 3x3 grid, and we want to insert the numbers 1 to 9 into the grid in such a way that the total in each row, column, and diagonal is the same. So if we just reduce this a little bit to what we're doing, we've got the numbers from 1 to 9, and we've got 9 boxes. Each number is to be used once and once only. You're not allowed any duplicates. Obviously, you can make all the totals the same by putting the same number in every box. You just put 4, 4, 4, 4, 4, 4, 4, 4, 4. No, that's not allowed. The numbers are all different. They've all to add up to the same thing. And I suggest to the pupils that before we waste an awful lot of energy, it might be a good idea to try and work out what this constant value is, the so-called magic constant. Now, if you think about it, imagine that we've managed to do this and the numbers are in these boxes. If you add them all up, you're just adding up the numbers from 1 to 9 in some order. And order doesn't matter for purposes of addition. So you end up with 1 plus 2 plus and so on up to 9. And eventually we manage to drag out of some pupil that the total for that lot is 45. Now, that total is distributed equally between the 3 rows. We'll talk about the rows, columns as well, but each of the 3 rows contributes equally to the grand total of 45, and therefore you come to the conclusion that the magic constant is 15, which means that if you put the numbers into the boxes in such a way that any row or any column or any diagonal does not add up to 15, the whole enterprise is doomed. Can't possibly work. So that's one thing that will save a lot of wasted time. One other thing that you might ask is, which number goes in the middle cell? What number goes in there? You ask the pupils for their view on this, and the most common choices are 1 or 9 or 5. Now, what about 5? I asked somebody. And they say, well, it's the middle number. It's the middle number between 1 and 9. So maybe, just maybe, the middle number goes in the middle cell. That proves absolutely nothing, of course, but it turns out to be correct. But sometimes you get an alternative explanation. Somebody will say, I chose 5 because it's 1/3 of the magic constant 15. Now that is actually a rather astute remark to come from people, and it turns out to be absolutely spot on. It is always the case that the thing in the middle there is 1/3 of the magic constant. I don't prove that when I'm doing a live presentation, but at no extra charge, I'm going to prove it for you just in a few minutes. So we've now got to the situation where we have a 5 in the middle there, and these various totals have to add to 15. And at that stage, I let the pupils loose with the comment that, surprising as it may seem, first of all, it can be done, and secondly, it can be done in more than one way. The general idea then is to see how many different magic squares we can get from the assembled company. And it turns out, as I prove just shortly to you again, that there are 8 possibilities. With a crowd of 200 in the room, there's a sporting chance that we'll get all 8 produced by somebody or other. that manages to do one quickly gets a prize. The prize is to find another one. And I say to them, see if you can find another one from the one that you've already got without starting all over again. So that gives them something to get on with, while others are perhaps struggling. So let me show you how we can go about this methodically. This is not what I do with the people. They just go at it, hammer and tongs, trial and error, and we end up with this, that, the next thing. After 15 minutes, all out effort, we stop, take stock, and see if we manage to get all 8. Let me show you why there are only 8. Now, first of all, let us ask, how many of the totals does each cell contribute? So we've got 8 totals to worry about. We've got the 3 rows, we've got the 3 columns, and we've got the 2 diagonals. So these are the 8 totals. To how many of these 8 does each of the numbers contribute? So if we go to a number in the top corner, whatever number is in that cell, it belongs to a row, it belongs to a column, and it belongs to one of the diagonals. And therefore, it's going to contribute to 3 of the totals. And that applies to all the corners. If we take a cell in the middle of a side, it belongs to a row and it belongs to a column, but that's it. And so these ones only contribute to 2 totals out of 8. And that leaves us with the one in the middle. And it belongs to a row and a column, but both diagonals. So the number that goes in the middle contributes to 4 of the 8 totals. So that's one piece of information. Each of the totals is made up of 3 different numbers from 1 to 9, adding to 15. So let's now see what sort of sets we can get that do that. We look for sets of 3 numbers from 1 up to 9, adding up to 15. We'll list them methodically, systematically, by means of taking the smallest in the set as the sort of label. And so suppose that we look for a set of 3 numbers adding to 15, of which the lowest is 1. Well, then the other 2 add to 14, and you can have a 5 and a 9, or you can have a 6 and an 8, but you can't have a 7 and a 7. You're not allowed to have it. And these, therefore, must appear somewhere in some order. I'm not suggesting that they appear in that order. That set of 3 is a possibility, and so is this one. If the smallest of the 3 numbers is 2, then the other 3 have to add up to 13. And the possibilities are 4 and 9, 5 and 8, 6 and 7 in some order. If 3 is the smallest of your 3 numbers, the other 2 have to add up to 12. You're not allowed 3 and 9, not allowed to repeat 3, but you can have 4 and 8, and you can have 5 and 7, but you can't have 6 and 6. If the smallest of your 3 numbers is 4, then you only have one choice for the other 2 adding up to 11, namely 5 and 6. And if you have a set of 3 numbers of which the smallest is 5, then the others are bigger than 5, and therefore the total is going to be greater than 15, and therefore can't work. So these are the possible sets of 3, and you'll see that there are 8 of these. We need 8 totals for our magic square, so every one of these sets of 3 must appear in some order in a row or a column or a diagonal. So let us now count the number of times that each of the digits 1 to 9 appears in these sets here. So we have the number 1, just a little bit. The number 1, I can just shrink it just a little bit more to get everything on at one time. Right, we've got it now, I think. The number 1 appears twice. There it is. The number 2 appears 3 times. There we are. The number 3 appears just twice. The number 4 appears once up there, once there, once there, 3 times. The number 5 appears there, 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 and there, 4 times. And it going on in this way, you discover that 6 appears 3 times, 7 appears twice, 8 appears 3 times, and 9 appears twice. Now let's put that information together with what we had up here. And let's in particular look at the middle cell. We're needing to put in there a number which contributes to 4 totals. So we go back down here. What number contributes to 4 totals? And the answer is 5. So that proves by a process of enumeration that 5 must go in the middle. Going back up here in the corners, we have things that contribute to 3 totals. Which numbers down here turn up 3 times? The answer is the even numbers, 2, 4, 6, and 8. So they've got to go in the corners in some order. And that leaves us with the odd numbers 1, 3, 7, and 9. And these are the ones that must go into the sides, midpoints of the sides. So this is an investigation I would suggest that could be done by pupils in S5 or S6, for example, not the P6, right? I don't do this in the live presentation, but this would be an opportunity for an investigation for pupils at the top end. So summarizing this thing, what we've got is 5 must go in the middle cell, 2, 4, 6, and 8 must go in the corner cells in some order, and 1, 3, 7, and 9 must go in the cells in the middle of the sides in some order. And that now enables us to work out the number of possibilities. Because in the top left-hand corner, go back up here, we have 4 choices, one of the even numbers. Once you've chosen that one, because 5 is already in here, that tells you what's got to go in down there, because these 3 have to add up to 15. So, with 4 choices for top left, each of which determines bottom right. If you look at the other 2 corners, top right and bottom left, you've got 2 even numbers left. Either of them can go in there, and once that's been chosen, that determines what goes in there. So with every one of the 4 choices there, you have 2 choices there. And do you see that that then finishes the job? Because once you know what's there and there, you know what's in there. It's got to add to 15. Ditto for all the other ones in the middle. So that proves, therefore, that the number of choices is 4 choices for that, going with 2 choices there. 4 times 2 equals 8. That proves again by just enumeration that there are precisely 8 magic squares using the numbers 1 up to 9. And as I say, that sort of thing is an investigation that could be done by some of the high flyers at upper secondary. Now, of course, when I'm doing this live, there are some poor souls who sadly, even after 15 minutes, have still not managed to find anything. So for their benefit, yours, first instance, I present this. Now, this is 1 out of 8. And this is a very famous one. This is called the low shoe. Now, that's spelled L-O-S-H-U. And it seems to be of great antiquity. The story goes that in about 650 BCE, somebody, some highfalutin Chinese person was wandering along the side of a river and saw this turtle, which had markings on its back, which purported to be the numbers 1 to 9 in some order. And so this has passed into folklore as being a very important 3 by 3 magic square, the low shoe. And we'll use this as a prototype for lots of things which are going to follow. But let's have a look at the complete family of 8. Here we are. Now, we'll use the low shoe. Here it is. I asked the pupils, suppose they got this one, how could you get another one from this without starting all over again? And they say, well, you've got to change things around in some way or another. And I say, well, make that more precise. And somebody will maybe point out, how about if we do this? Rotate the thing through 90 degrees. The rows turn into columns, the columns turn into rows, 5 stays that's where it is, the totals are unaffected. So here is the second magic square, 8, 3, 4 in the top line. And of course, anything that works once, we do it again. I don't know if we've got any of our friends from Australia still with us, but here we are upside down now, and we've got 618 along the top. And this is such tremendous fun that we can turn it around again. And we've now got 276 along the top. And we can turn it around again, and we get back where we started. And so to summarize the story so far, from the original one, by rotating through 90 degrees 3 times, we pick up these 3. But then we have another bright idea. Imagine that the middle column, for example, could do it for the middle row as well, but let's do it for the middle column, regard it as a mirror and reflect. So send the first column over to the third column and the third column over to the first. This one here turns into this one here. And if you do the same trick on all of these, just reflecting each time, you get the rest of the family. So we can say that in this low shoe family of 8, you can get any one of the 8 from any of the others by a mixture of rotation and or reflection. So you could almost say that there's basically only one 3 by 3 magic square using 1 up to 9, and all the rest are derived from it. Now, we come to some stuff that I didn't know until about 8 years ago. This arose from the after-dinner speech at the 2013 Maths Association Annual Conference. The after-dinner speaker was Professor Art Benjamin, who is from Harvey Mudd College in the United States. Not only is he a mathematician, but he's also a magician. And he put on a terrific show for us at this after-dinner speech. If anybody wants to see this man in action, there are plenty of things out there on the internet. If you just Google Art Benjamin mathematician, put in mathematician, because there's an Arthur Benjamin who is a composer of classical music, and doubtless plenty of Arthur Benjamins as well. But if you put in Art Benjamin mathematician, you will find some of his performances, and they really are performances. He was doing things like multiplying 3-digit numbers together in his head and so on and so forth. But there was a spot on magic squares. And he drew attention to the following. So here we are, we're using the low shoe as our prototype, but what I'm saying for the low shoe works for all the other 7 that we had a moment ago. Look at the numbers in the first row. Take their squares, 4 squared, 4 times 4, plus 9 times 9, plus 2 times 2. Add up, you get 101. Do the same for the bottom row. 8 squared plus 1 squared plus 6 squared. That also adds up to 101. Don't try it on the middle row, it doesn't work. Right? But first row and the third row, sums of the squares are equal. And of course, as you would expect, what works for rows, columns. So if you take the first column, 4 squared plus 3 squared plus 8 squared, plus 2 squared plus 7 squared plus 6 squared, they turn out to be the same as well, 89. Let's just park that for a minute and we'll come back to an investigation into why that might be general. Now, if you next take each of these, and imagine that working in base 10, you use them to form 3-digit numbers. So we now look at the numbers 492, 357, and 816, and you add them up. You get 1665. If you reverse all the numbers, so that you get the 3-digit numbers 294, 753, and 618, and you add them up, you get the same answer. Now, how does that grab you? Maybe you think to yourself, that's maybe no big deal, because we had all this business of reflecting and so on. However, stay tuned. But before we stay tuned, I draw your attention to 1665. I don't know how your history is, but that was the year of the Great Plague. So I think it's somewhat ironic, given the current situation, that we get this number 1665, the year of the Great Plague, turning up. There it is. But now I present for your delectation and delight the following. So once again, we have the numbers in the normal order, and here we have the numbers reversed. This time we're going to add the squares together. So 492 squared plus 357 squared plus 816 squared versus this squared plus this squared plus this squared. These two things turn out to be the same. 1,035,300. What right have you to expect that? Well, it depends on your point of view. There are people around, far too many, who seem to think that a plus b all squared is a squared plus b squared. So if you're a member of that version of the Flat Earth Society, then this will be no big deal. But the rest of us remember that this is a matter of 2ab as well, which jiggers up a lot of things, but on this occasion it doesn't. So what's going on here? Lots of funny things going on. So let me now show you. Now, if anybody wants to switch off for the next 5 minutes while we do a bit of algebra, you can tune in again just shortly. But I would like to show you what lies behind some of these things that I learned. Because having been exposed to all this at this after the speech, I thought to myself, I want to find out what's going on here. So what I'm going to do now is to take a completely general 3 by 3 magic square. So we've got a set of 9 numbers just labeled A up to I. So not necessarily 1 to 9 anymore. So these could be positive integers, no longer consecutive. They could be negative integers. You could even have fractions, I suppose, if you want. But let's assume, just to fix ideas, that these are 9 distinct positive integers. I mentioned this astute remark or suggestion by a pupil that the thing in the middle was 1/3 of the magic constant. Let me prove that that's always true. So here we are. Let's assume these numbers do indeed form a magic square. Its magic constant is m. Look at all the totals involving the thing in the middle. So it belongs to this diagonal. So therefore a plus e plus I must be m. It belongs to the other diagonal. C plus E plus G must be equal to M. It belongs to this column. B plus E plus H must be equal to M. And it belongs to this row. So D plus E plus F has to be equal to M. We now find ourselves with 4 equations, and a common trick that crops up very often, for example, in competition problems, is to add the whole lot together. So if we add these 4 equations together, we obviously end up with 4m on the right-hand side. What's happening on the left? Well, you see, E appears 4 times, obviously, that's by design. But each of the other letters appears precisely once. So we can write the following. We've got one lot of A, B, C, D, F, G, H, and I. And we split the 4 lots of E into one of them, sitting in there, and the other 3 sitting out here. But now you see A plus B plus C is the first row. Where's that thing disappeared to? That wasn't meant to do. There we go. A plus B plus C is just the first row. So the first 3 in there add up to M. And the next 3 add up to M because that's the second row. And the third lot add up to M because that's the third row. So this is M plus M plus M. 3 lots of M in the brackets. Plus 3E equals 4M. And therefore, M equals 3E, E equals M over 3. That's something else you could give to pupils at the top end of the school. It's quite easy once you have the insight. You need a bit of insight here, the insight being to write down these 4 equations and then add the whole caboodle up. Now, you'll notice I mentioned when we formed these numbers like 492 in base 10. You can actually do it in any number base if you're inclined. If you want, for example, to do hexadecimal or even scale 60 or anything like that. It turns out that everything works. So previously, just to fix ideas, we had 492, and we had 4 times 10 squared plus 9 times 10 plus 2 to form the number 492. Suppose we take the general setup and use base x. So the corresponding numbers would be a lots of x squared plus b lots of x plus c, and ditto for the other 2. And you see, when you add these up, you get coefficient of x squared is this, the coefficient of x is this, the coefficient, or the constant term, is this. But then you see this is precisely the first column. So this lot is m. This is the second column, so that's m, and this is the third column, which is m. So you get m lots of x squared plus m lots of x plus m. M is a common factor. You're left with x squared plus x plus 1. Now, in case anybody's getting completely lost, let's go back to what we had before. M was 15, x was 10. If you exit the 10 into the brackets, you get 100 plus 10 plus 1, which is 111. And if you multiply by 15, you get 1665, the year of the Great Plague. So this is just a generalization of this. And the fact that these letters have disappeared and we're left with just nothing involving the letters shows that you can swap around these columns like I did before, and everything is okay. Now, back here, we had this business. Let's look at the first and third column. We had this 4 squared plus 3 squared plus 8 squared equals 2 squared plus 7 squared plus 6 squared. Let's see what the analog of that would be here. We'd use the first column, a, d, and g. So a squared plus d squared plus g squared equals c squared plus f squared plus I squared. That would be analog of that. Now, let me just show you quickly why that works. Look at this diagonal. A plus E plus I equals M. But we have proved that that is a third of M. So therefore, A is M, the grand total, minus M over 3 from there, minus I. This is using something we've already proved. And you do the same for D versus F, using the row, and for G versus C, using the diagonal. We substitute for each of the things here in terms of things over here using the fact that E equals M over 3. And now we have to do a wee bit of algebra here. Again, this is something that would be at the top end of the school, but might not be beyond, I hope. These two combine to give 2/3 of M minus I all squared and different for the other two. Expand all these brackets out, so you get 4m squared over 9 minus twice first times second is 4 times mi over 3 plus I squared, and same for the other two. You gather the terms in m squared together. We seem to have 3 lots of 4/9, which gives you 4/3. And then we've got the terms in m have a common factor of 4m over 3, and this one has an I, this one has an F, and this one has a C, so we get to this. And then we get I squared plus F squared plus C squared for the constant term. And now, I plus F plus C. What is I plus F plus C? It's the third column added up. So that bracket is equal to m. And now see what happens. These two terms cancel, and you're just left with this. So what we've done there is taken a previous result, E equals 1/3 of m, to prove the next result. A squared plus D squared plus D squared equals C squared plus S squared plus I squared. So what we're doing here is similar to what we did in the good old days when we taught Euclidean geometry properly. You started out with some various postulates, axioms, conditions, or whatever, and you started proving theorems. And once you proved a particular theorem, you then use that theorem to prove another theorem. So what we're doing here is we're building on what we've done before. And this result can then be used to prove the next result. that this extraordinary thing that we had back here, that I suggested that you had no right to expect, this thing here, in terms of the general number bases, we get the numbers ax squared plus bx plus c, dx squared plus ex plus f, and so on and so forth. So we want the sum of these squares with the numbers in the right order to be the sum of the squares when they're reversed. And to draw a veil over that, what it boils down to, when you expand out these things, you get things that you can for equate coefficients. You discover that the coefficient of x to the fourth in the first row is this, and the coefficient of x to the fourth in this is that, and these two are equal by what we've just proved. So you see what's going on here. We're building up a whole variety of results, each one depending on the other. Now, I could go on like this all afternoon, but I don't know whether there's anybody still left or whether you've all left, because that's been too much for you. So we'll now abandon all that and do something completely off the wall. So if there's anybody who's fallen asleep, now you can tune in again. Have a look at this. What we have here is a new magic square. I'm made up with a low shoes. Let's have a look. You can see that, well, first of all, the numbers aren't consecutive anymore, but a quick check will show that this jolly thing is a magic square with magic constant 45. That you can easily check. Right, now I'm going to do something completely zany. I'm going to replace each number in this affair by the number of letters when you spell it out in words. So in other words, here is 5. F-I-V-E. 4 letters. So I'm going to replace 5 by 4. 22. Okay, there's 6 letters in 20. There's 3 in 2, so that's 9 letters. Never mind about the hyphen if you've bothered to put it in the first place. And 18 has got 8 letters, right? So we do all this and we arrive up with this grid, right? So that's what's happened, where you just replace each thing in the first grid by the number of letters. And guess what happens? This thing is, amazingly enough, a magic square again, with magic constant this time 21. So what we've done is we've started in the maths class, gone off into the English class, done a spelling lesson, and produced this thing, and lo and behold, it's another magic square. Now, of course, this, needless to say, is a complete fluke, and there are people out there who spend their whole lives dreaming up curiosities like this. It's totally useless, of course, but I think it's rather cute. And I'm going to use it to prove one or two, or show you one or two other things. Here's this first one again. It's the same one as we had here, just again. And what I'm going to do this time is I'm going to replace each number by its place in the pecking order. Right, so we've got 9 distinct numbers here. So the smallest one is 2, so it's going to get replaced by 1. The next smallest is 5, so it's going to get replaced by 2. The next smallest is 8, which is going to be replaced by 3, and so on. And if you do that, you arrive at this. Look at this. We've seen it before. This is one of the low shoe family. You can't get rid of them. Let's do this. Let's take the silly one that we got up here by counting letters. Let's bring it down here. Here it is again. And this time, subtract 2 from every element in here. So 4 minus 2 is 2, 9 minus 2 is 7, and so on and so forth. Guess what that produces? It's the same one back again. So this low shoe family is never far away. In fact, you can say the following. If you kick off the 3 by 3 magic square, where all the numbers are different and they're all positive integers, and you replace the number in each cell by its position in the pecking order, increasing order, then you always end up with one of the 8 magic squares in the low shoe family. And since they're all essentially the same, you can almost say there's basically only one 3 by 3 magic square involving integers anywhere. They're all related. One. Now, in contrast to stuff we've been doing for 3 by 3s, this last thing we did up here, subtracting 2 and so on, that works in general. If you've got an n by n magic square, the magic property is preserved if you add the same constant to each entry, or you subtract the same from each entry, or you multiply or divide each entry. by the same non-zero constant. So you see, what we did up there was we subtracted 2 from everything. You could add 15 to everything, or you could multiply everything by 3 or whatever. That would trade in one magic square for another. But we'll not go down that route. One final appearance of the low shoe. And this is for definitely the top end of this school. Matrix multiplication. So if there's any primary people still around, just hold on. Culture is just around the corner now. Take this thing as a 3 by 3 matrix, 492357816, and work out by matrix multiplication the square. So it turned out to be this. Now take a look at this thing. This is most definitely not magic, because you can see immediately that the sum of the diagonals, it's down that diagonal, you've got 359s, and along this row you've got 159 and 283s, so that's no use. But look what happens if you keep going and you work out a cubed. It turns out that a cubed is magic. A squared isn't, but a cubed is. And guess what its magic constant is? It's the cube of the magic constant of a, 3,375 if you like, but 15 cubed. And there's more, because if you have a matrix here which is invertible, as this one is, and you go looking for its inverse, which you calculate by whichever means you like. Here's the inverse of low shoe. Here it is. That's 360 thing. This means take all the numbers in there and divide them all by 360, which is the determinant of A. Then it turns out that this is again a magic square whose constant is the inverse of the magic constant of A. And it turns out that this is true for any 3 by 3 magic square whose matrix is invertible. And the other one is true in complete generality. This one up here, which doesn't rely on invertibility, is in fact true for any 3 by 3 magic square, connection with matrix multiplication. And this is something which is absolutely intrinsic to 3 by 3. There's no corresponding 4 by 4s. So what I've shown you so far is a whole collection of odds and ends, curiosities, if you like, but things I think which are rather beautiful. In the time that's left, I think I've got about 10 minutes by the clock, we will wander off into slightly larger magic squares, and this is just going to be culture. We're not going to prove anything here. I just want you to marvel at what we've got here. Here's a very famous 4 by 4 magic square. It's the numbers 1 to 16. And you can easily check that each row, column, and diagonal adds up the same thing. The magic constant this time is 34. But this has an extremely rich structure. If you take the 2 by 2 block up here and add the numbers in there, that lot add up to 34. If you take the 2 by 2 block there, these add up to 34. This 2 by 2 block adds to 34. This 2 by 2 block adds to 34. And the 2 by 2 block in the middle adds to 34. And if you want, you can find various other collections add to 34, things down to diagonals and so on and so forth. So it's got a very rich structure. And there are things in here which are analogous to what's gone before. But what makes the thing even more amazing is what I'm showing you down here. You'll notice, if you wish, watching in black and white, that these here have been highlighted in red. And that is for the following reason, and this is what makes this magic square so famous. It appears in a work of art by a German artist called Albrecht Dürer. He produced an engraving called Melancholia. You don't need to be a Latinist. And in that engraving, this magic square appears, which is interesting enough. But the coup de grace is that the year in which he did this engraving was 1514. So he manages to get the year in which he did this work of art into the magic square. So I think in terms of beauty and joy forever, this takes some beating. I mentioned that there are some things that carry over from the 3 by 3 case. For example, if you take the first row and the final row, and do the sum of squares, because 16 squared plus 3 squared plus 2 squared plus 13 squared is in fact equal to 4 squared plus 15 squared plus 14 squared plus 1 squared. But there's a bonus, because if you do the sum of the squares of the second row, it turns out to be the sum of the squares of the third row, and so on and so on. There are all sorts of things going on in that. Lots of other interesting problems. So that would be an investigation. Again, somebody could almost write a little essay all about this 4-by-4 magic square. And this will attract the attention of all sorts of people, because the next thing that happens is that somebody has used magic squares to write a piece of music. Sir Peter Maxwell Davies is, or was, because he's sadly no longer with us, a classical music composer. He was the master of the Queen's music and actually spent the latter years of his life on the island of Hoy, in Orkney. He used an 8-by-8 magic square to construct a piece of what you might call music. Now, this is not a very tuneful piece of music by any manner of means. It makes use of what's known as 12-tone technique. I'm not going to attempt to explain all that. But what I would do is to say that it could be that there are some people who are interested in both maths and music. And I'd like you, those people might be interested to go to a certain lecture. And to tell you about this, I start with the Gresham Professor of Geometry. Gresham College in London is a venerable institution which has existed for well over 400 years. And it has had a professor of geometry all the time. Obviously not the same person all the time, but this chair has existed all those years. One of the duties of the Gresham Professor of Geometry is to give public lectures. The current professor of geometry, believe it or not, is the first lady to hold this post in all those 100 years. Her name is Professor Sarah Hart. She's been giving these public lectures, but obviously because of the epidemic, they haven't been live in the sense of an audience, but instead they have been streamed. And the first one of the series was called The Mathematics of Musical Composition. And in that, about 46 minutes in to be precise, she has shown, using the Dürer magic square, how Maxwell Davies and others have used magic squares to compose music. So if anybody is interested in this, all you need to do is to Google Gresham Professor of Mathematics, and that will take you straight to Sarah Hart and her lectures. So there's art and music polished off. There's more culture in the last 5 minutes. Let's speak out now to 8-by-8. Now, I present the students in the back out in the hall with all these pupils, and I present them with a blank 8-by-8 grid and ask them, if fresh from their success with 3-by-3, they might like to have a bash at an 8-by-8. And of course, there is a hostile reaction, you can imagine. But I say, don't panic, I just want to show you a couple of them. So here's exhibit 1. Using the numbers 1 to 64, trust me, this is a fully paid up magic square. The magic constant is 260. This time, that's a bit like the silly thing we did with turning 5 into FIVE and so on a few minutes ago. What I'm going to do now is to replace each element by its square. So you would replace 7 by what? And I ask the people what that is, and they say 49, jolly good. And then I ask them, and then we're going to replace 53 by 53 squared, and of course there's a deathly hash. Nobody has a clue what that is nowadays. Those of us of a certain antiquity used 4-figure tables, and we opened this book every day at the same page, and so by a process of osmosis we'll learn the squares of the first 100 positive integers, 2,809 in this case, and so on. So we replace every number and end up with a new 8-by-8 array. Would you believe that that is also a magic square? It is. And this was created by a gentleman called Benjamin Franklin. So I asked the students if they know anything about Benjamin Franklin, and we get some very interesting suggestions. One of the most popular is that he was president of the United States. He wasn't president of the United States. He was one of the founding fathers. But then I asked them, anything scientific you know about Benjamin And sometimes we're in business because somebody will then tell us about the story of him flying a kite in a thunderstorm with a key on the string and discovering that lightning was a form of electricity. He was a real polymath. He did all sorts of things, and he loved making up magic squares. In his day job as a sort of politician, he found himself in so many boring meetings that he would often just opt out of the meeting and go away and make up a magic. He just hundreds. And the last exhibit, this. Again, we've got the numbers from 1 to 64, and this is almost but not quite a magic square. The rows and columns are fine. They add up to 260 as they should, but the diagonals misbehave. So this is what's called a semi-magic square. So basically, why am I presenting to you something which is not the finished article? Well, have a look at how we get from one number to the next. So there's 1, there's 2, there's 3, there's 4, there's 5, and so on. And I ask the pupils, can they see what's going on? And sometimes somebody will spot immediately, but sometimes I have to give them a hint. The hint is, where else in life do you see an 8 by 8 grid? And the hope is that somebody will come to a chessboard. And then we ask, what sort of pieces exist on the chessboard? And how do they move? And with that prompt, somebody will realize that to get from each number to the next, it's a knight's move every time. You get right round the board, visiting each square once and once only, completely by knight's moves. It's what's called a knight's tour. And this particular one was concocted by Leonhard Euler, no less. So here we have an array, which is a fully paid up knight's tour and almost but not quite a magic square. Could we do better? Is there another way of putting the numbers in the boxes in such a way that we end up with something which is again a knight's tour, but is also a fully paid up magic square? Well, the number of knight's tours is known. It's a 14-digit number. 13,267,364,410,532 to be precise. Somebody has worked that out. So it's a large number, but it's a finite number. The number of 8 by 8 magic squares is unknown. Nobody has a clue. Even for 6 by 6, we know that the number of 6 by 6 magic squares is of the order of 10 to the 19th, but nobody knows exactly what it is. So 8 by 8, nobody has a clue. But we do know how many knight's tours there are. So what you do now is you get a computer, and get somebody to program it, and it can then crank through all the knight's tours and discover whether any of them are magic squares. And the answer is no. None of the knight's tours is a fully paid up magic square. In fact, what we've got here is the best you can do. So there we are. No knight's tour is a magic square. That's one thing less to worry about when we go to our bed tonight. It's no use to man or beast, and that probably applies to almost everything I've said, but I hope that you've enjoyed the night and seen some things which I think are just beautiful. They involve some beautiful ideas, and suggest there are a number of investigations that you could give to your better off students. So it's been a long day, I know, for everybody, but if there's anybody still out there, there seems to be 43 of you. Thank you very much for lasting the course, and all the best. Thank you.
Thank you, Adam. Absolutely brilliant way to end the day. There's been lots of chat in the